you wish, you can ignore this term, and plus and equal to Fk. Here you can also have the UK P minus 2 UK plus Fk UK P minus 2 UK. Okay, so this is what that you're going to get actually. Alright. What would be this first term? So there are some calculations that I'm going to leave for you, and for some calculation I'm going to directly use the reference actually. So rather than repeating the calculation, you can see the calculations from there. Okay. So this can be written as, I can pull this derivative out, time derivative out. So the penalty would be multiplied by the 1 over p, and then you're going to have UK inner product of UK with UK power p minus 2 and UK. So it's going to be the d by dt of UK LP naught. So this is what that you're going to get actually. Okay. And obviously raised to p. Okay, raised to p. So 1 over p d by dt UK power p. So in other words, you pull 1 over partial by partial t out, so you need to pay the penalty 1 over p and then integrate, so you're going to get actually this. So just multiply UK and UK power p minus 2 and UK, and you're going to get this actually. This is also pretty much straightforward. So this will become what? So this will for sure become no. I must write it correctly, that it should be UK power p minus 2 and UK. Okay. And it's in the product. Plus, let's call this next term as n of mu n of UK. I'm just gonna directly mention them. Plus 4 mu p minus 2 by p square and m of, what do you call, UK, and equal to, and take for example these both terms on the other side and call each one of integral as I1 plus I2. So let me write it explicitly, where here n of UK, that is basically this term, can be explicitly written as, so you have to think a bit carefully, explicitly written as integral over R2 of gradient of the UK power p minus 2 times UK. Okay, so the gradient of square, okay, Laplace, the gradient of UK square times UK power p minus 2. Okay, so this is what that you're going to get. Okay, where n of UK is this term, and my claim is that if you simplify this, you're going to get this. So think for yourself that why this integral simplified would give you this actually. Okay. Okay. So what is the next thing? The next thing that I am interested in to show you both of these terms. So the third term has been written like this. It's also not difficult to show. Let's give it a name, say m of UK. So m of UK is this term, okay, and you have to think carefully and try to figure it out. that m of how this term can be simplified and written as an integral over R2 of the absolute of the gradient of the UK power p over 2 absolute and dx. Obviously, this integral is also with respect to dx. Okay. While for I1 and I2, so these two you have to figure out for yourself actually, that why this is true. Otherwise we can discuss it in tutorial actually, that okay, why this calculation is simplified, or this can be simplified to this and this can be simplified to this actually. Okay. Now for the rest of the two terms, this and this, I'm gonna use this, what do you call, reference again. So in these reference for I1 and I2, in other words, these two terms, not plus but equal to, for these two terms there are some estimates already given actually. So the I1 can be estimated by a constant c, so p minus 2 square over mu and uk power p plus 2 l p plus 2, okay, and I2, the estimate for I2 goes like LP norm of Fk times LP norm of UK raised to p minus 1. Okay, these are the two things. Now, what is next thing? So we had estimate actually. Next, I would like to simplify these two terms a little bit more. Okay, and for that I'm going to use the Gagliardo-Nierenberg inequality again. Gagliardo-Nierenberg inequality again, and by using the Gagliardo-Nierenberg inequality for n equal to 2, and let's apply the Gagliardo-Nierenberg inequality to a function gk, that gk is uk absolute of uk power p by 2. Okay, and I want to apply the following version of Gagliardo-Nierenberg inequality, that goes like gk raised to lp plus 2 over p 2 times of L 2 times of p plus 2 by p. Okay, that can be estimated by c times of the gradient of gk in h norm raised to 2 by p plus 2 times norm h norm of gk and raised to p over p plus 2. Okay, so p over p plus 2. So this is what the version of Gagliardo-Nierenberg inequality that we need to use in two-dimension actually. Okay. So again you need to take j equal to 0 and m equal to 2. Your p is going to be this actually in Gagliardo-Nierenberg case, and your q and r are going to be 2 because these are L2 norms actually. Okay, so they are going to be 2, and m is going to be 1 because this is the first order derivative. So using the suitable exponent, this is a good exercise for you to figure it out that, okay, what exponent should I choose so that I can have this Gagliardo-Nirenberg inequality, this version of Gagliardo-Nirenberg inequality. Okay. So what's the benefit of having this Gagliardo-Nirenberg inequality? By the way, let's say do a little bit of calculations and calculate each one of these actually. So what would be the GK L P plus 2 times of P plus 2 norm by P. Okay, so what would be this actually? So this is going to be the integral over the entire R2 of GK raised to 2 times of P plus 2 by P and everything raised to the reciprocal of this actually. So the P by 2 times of P plus 2. Okay, so this is what that you can get. But what is GK? The GK is UK, absolute of UK raised to P over 2. Okay, this is what it is. So if you simplify it, okay, so you're going to get inside R2 and UK raised to P plus 2 and everything raised to P raised to 2 raised to P plus 2. Okay? And this guy, I can say that this is equal to UK LP plus 2 norm of UK power P plus 2 actually. So this inside can be written as this and then everything power P over 2 times P plus 2. Okay, so these are little calculations actually. So this P plus 2 and P plus 2 will go away. So the GK raised to, this is going to be UK power LP plus 2 and raised to P over 2. So this is what that you're going to get actually. Okay, so what would be the next thing? So the next thing that is going to be is to really see this gradient of G L2 norm raised to 2 over GK 2 over P plus 2. So if I simplify it, so it's going to be integral over the full space R2 of the gradient of UK power P upon 2 and everything raised to 2 and everything raised to 1/2 times this power, which is 2 over P plus 2. So the 2 will go away and we're gonna remain with the gradient of R2, gradient of UK raised to P by 2, okay, and everything raised to, what do you call, this 2 and then raised to P plus 2. Okay, this is what that you're gonna get. And this is what that you're going to get actually. And with the notation, I mean, if you remember, we called this guy is M of UK raised to this actually. So So what does this show? So if this guy is m of uk, so everything that you're gonna get is m of uk raised to 2 by p plus 2. So this is what that you're gonna get. So your gradient of gk. What would be, this is the gradient of gk raised to 2 over p plus 2. So the next thing is to say, for example, do gk and it's L2 norm raised to p over p plus 2, p over p plus 2 would be inside, not outside. So it will be square, and then it is going to be 1 over p plus 2 actually. Okay. And here you also have a square actually. So this is going to be m of uk power 1 over p plus 2. So you have to be a bit careful actually. These are some of the nasty calculations. So the gk power p plus 2 is going to be what? We need to integrate over r2 gk, which is uk power p over 2, and it's a square, and then it's 1/2, and then this p raised to p plus 2. Okay, so you can get rid of this 2 and 2, and what is going to remain inside is really the LP norm. Okay, so I can call for the integral over R2 is the norm of UK power P raised to P actually. So I can write this as norm of UK and its LP norm raised to P. Okay, raised to P, and then raised to 1/2 times p over p plus 2. Okay, so if you simplify this, p over p plus 2. So if you simplify this mess, you should get what do you call UK power p square by 2 times of p plus 2. Okay? You don't have to rely on my calculations. You can reproduce these straightforward calculations for yourself actually. Okay. What is the next thing? The next thing is to substitute all of these three into what you call the Gagliardo-Nierenberg inequality. So this side becomes what? UK power, LP plus 2 norm of power P by 2 can be estimated by m of UK raised to 1 over P plus 2 times the last term that you're going to have is the LP norm of UK raised to P square divided by 2 times of P plus 2. So this is what that you're going to get actually. Okay. So more you can do is that I can try to turn this power into P plus 2. So what if I want a power P plus 2 here? So the first I need to multiply the power by P plus 2 and divide by 2 over P. So P plus 2 times 2 over p. Okay, so take power p plus 2 times 2 over p on both sides. Okay, so what are you going to get? So you're going to get uk raised to p plus 2 lp plus 2 times. So if you're going to get p plus 2 and p plus 2, so you're going to get m of uk raised to 2 over p. So I hope I have, yes, got it correctly. And if I take power, what do you call, this p plus 2 times 2 over p, so you're going to, what is going to remain is uk raised to, what do you call, power p, and obviously the constant c. So this is what that you're going to get actually from the Navier-Stokes inequality. Alright. So why we are doing all this mess? Let's call this as inequality A. Is another obvious inequality. You can think that why you have this inequality. That if you take any x from R2, then the gradient of any function uk raised to p over 2, and it's as absolute. So what would be the gradient of uk power p over p minus 2? So it's going to be p over 2 times p over 2 minus 1 times the gradient of uk times the sign of, what do you call, absolute. In other words, you can estimate, so you can think of thinking that why this inequality is true. So the p over 2 uk power p upon 2 minus 1 times gradient of uk. Okay, so the gradient of uk. So this is what is inequality. So what I'm going to do inequality, if you give this inequality, I want to apply a Young inequality. So what is the Young inequality? The version of Young inequality, Young's inequality that I would like to apply is the following version. So that goes like this. So AB can be estimated by epsilon times a plus b, a power b plus c epsilon, constant that depends on epsilon times, we call b e prime, and p is between 1 to infinity, and 1 over p plus 1 over prime is 1. Okay. So this is what that I would like to apply, and there is a value for the constant epsilon as well, which at the moment I am not interested in. So what I would like to show now. So before applying the Young's inequality, so we had this inequality, and we also talked about a little bit of this inequality. So what I would like to do is that I would like to use these two inequalities and deduce an interesting version of inequality. So the UK LP plus 2 power P plus 2, that is less than or equal to, what do you call, C of MUK, C P of what do you call MUK, and if you remember, the value of M of UK is the gradient of UK power P over 2, okay, and raised to, and obviously it's square dx, and its power is 2 over p, 2 over p times the second term is as it is, so the UK raised to UK UK and it's LP norm. Okay. So this is LP norm actually, yes. So you have to be always careful about the things. So the LP norm raised to P. So this is what that you have. Now if in this integrand I use say this inequality, so I'm gonna get what? So I'm gonna get this actually. So I'm gonna get C over omega. This is less than or equal to, what do you call, P over 2 UK power, what do you call it, P upon 2 minus 1, okay, and raised to and what, and the gradient of UK, and square over it times, I must write this a little bit better, UK power P and P. So what I did, I took this asterisk